So, yesterday, well, a lot of technical problems yesterday, right? Problems and technical problems. But today, hopefully, things are going to be more straightforward. Most importantly, because we're in the same room as the computer's in that room over there behind that door. If we have any technical problems today, we can just open the door, press the button, and the computer should come back to life. Okay? So I don't anticipate any big problems. But what I want to do first is just have a look at what we said yesterday. The first thing was that if we want to simulate a crystal, we need a Bravais lattice and we need some symmetry operations. Okay? We said that earlier on yesterday. And in order to do that, all we need to do in the ASE package is to build a bulk crystal. Okay? This is FCC Palladium. We're viewing the conventional cell, not the primitive cell. And what we've done is we've set up a so-called calculator. So ASE is a generic piece of Python software, a generic Python library, which interfaces between DFT packages in general and Python in a Jupyter notebook. You don't have to use a Jupyter notebook. I should note, some people yesterday wanted to use PuTTY or SSH. This is fine. You can do all of this in PuTTY and SSH if you want to, but the difference is you need to make a file and run it with Python rather than run it through Jupyter Notebook. So just before we do anything else, I just want to do that. I just want to show you. How I would do it if I was logging in with SSH and I wanted to use ASE. So I'm going to enter the same directory and I'm going to make a new directory inside of that directory called, I don't know, SSH. All right. And so in SSH, all I need to do is load a text editor. So I don't know, you can use any text editor you like. Your favorite might be VI or Vim or Nano or whatever. How do I say? Or whatever you like. But my favorite is Emacs, so I'm going to use Emacs, right? So what I'm going to do is just script.py. I'm just going to edit a file called script.py, and I'm going to just do the same commands that I entered in the Jupyter Notebook yesterday. So I'm going to do from ASE.build import bulk, from ASE.calculators .castep import castep. And in fact, why don't I just copy and paste rather than wasting time doing that, right? So what I'm going to do is that. Okay, so I have a little script there. You can see in my directory called SSH, I've got that script, and I can just run that script. Okay, all right, module's not defined, fine. Right, so I should explain, because a couple of people had problems with the module command. So the reason that in the Jupyter Notebook, I have made that module load automatically, or I should have done, I fixed it. The reason that it should load automatically is because that's my module, right? If you use a different computer, this command will not exist, right? Because I made that specific for this computer. So I didn't want to put that too prominently in the script, because it might confuse people if they move to a different computer and they're like, well, where's the module command? Well, this is specific to this computer. On other computers, you don't need to do it, or they may give you a different command to use, right? But on this computer, I'm just going to load this environment, my module, modules, import module, right? Okay, so that line from environment modules import module. That was the problem that people were having yesterday, because in the Jupyter Notebook, that is supposed to load automatically. Okay. Right. So with that out of the way, I can run that script. Environment modules is not available. All right. So this is just a problem for this computer. So what I'm going to do is just get rid of that completely. And what I'm going to do instead is just load it in the path here. I'm just going to say module load compchem/castep. Run it again. Okay. And so now it's running the script that we were running in the Jupyter Notebook, and it's going to run the castep calculation from SSH or from PuTTY. Okay. So I'm not going to run it all the way through. I'm going to stop it. Okay. I'm going to kill it, and I'm just saying, if you prefer to do it that way and you don't want to use the Jupyter Notebook, you can do that. Okay, your choice. Okay, but because it's easier to see on the screen, and because it's easier to sort of debug in front of you, I'll use the Jupyter Notebook here. Right, so let's begin. So yesterday, as a recap, we did this calculation where we set up a bulk palladium conventional cell, FCC conventional cell, and we ran a basic castep calculation. We ran LGA, we ran PBE, and we explored different basis set precisions. Okay, basically different cutoff energies for our plane wave basis. And what we said was, we can set up one of these calculations which has a particular Brillouin zone sampling, K-point sampling, in this case 2 by 2 by 2, and we can loop over these cutoff energies. Okay, we can loop over cutoff energies. What you can see here, if we look at the total energy, we can look at the difference between 300 eV and 400 eV, and we can see that the difference is, well, what is that, about 80, no, it's negative. Well, maybe about 80 eV different. And then we go 400 to 500 difference. And so we're looking at about 10 eV, and then about 2 eV between 500 and 600, and then we're down to 0.07 by the time we're 600, 700 difference. Okay, so because I put all of this data into cutoffs and energies, right, we can take a look at energies. All right, okay, it's no longer in memory because it was yesterday and I killed it, but we can take this data and we can put it into memory as if it was in memory like yesterday. Right, so what I'm going to do is just take this data. So yesterday, this would have just been in memory after the calculation finished. Now I'm going to put it back into memory. Right. All right, and I'm going to say energies equals that list. Okay, and if I pause energies, okay, I can see those are the energies that I got out of the calculation. And what I'm going to do is just diff that. Diff energies. Right, and so this expresses easily the difference between 300, 400, 400, 500, 500, 600, etc. And so you can see the difference between the first two is about 80. The difference between the second two is about 10, then about 2, then about 7 times 10 to the minus 2. Right? So the question is, at what point do we consider it converged? All right? At what point do we consider it converged? This thing. So what we were saying yesterday was that our energy should look something like that, and when that difference between this point and this point, say that's 600 and that's 700, once the difference between those 2 points is small enough, we can consider it converged. We can consider that flat, right? But the question is, what is converged? And it's completely arbitrary, right? What you have to ask is, I want to calculate an observable. I want to calculate something which is which I'm going to use to predict experiment. Okay, what accuracy would be good enough? Right. So if you're, for example, predicting surface energy, right, or work function on a surface, and you need to calculate work function to within 10 to the minus 2 in order to be able to predict something from experiment, because the experimentalists say to you, right, this system has a work function of x, and this system has a work function of y, okay? And the difference between those two work functions is, I don't know, 10 to the minus 1, right? EV. But we need to know why this one is higher than this one. Can you do a calculation on both of these systems and look at the difference, right? Well, it's pointless and worthless for you to do a calculation with an accuracy of less than 10 to the minus 1, right? Because then it's not going to predict the experimental result, okay? So this is how we decide when it's converged. We think, what would be good enough in order to predict something from experiment? 10 to the minus 2 would be good. We'll stop at 10 to the minus 2. In general, most things that I calculate, well, most energies that I calculate have an accuracy which is good enough at 10 to the minus 2 EV. Why? Because most experiments are not that accurate. Okay, 10 to the minus 2 is usually accurate enough to be predicted. So that's my rule of thumb. That's what I would normally stop at, 10 to the minus 2. But if you have a particularly accurate experiment, be very careful, right? Because just because your plane wave basis set is converged at 10 to the minus 2 doesn't mean that your calculation is predictive to 10 to the minus 2. Because we have to remember that the difference between our real quantum mechanics and DFT, it also has an error associated with the exchange correlation functional. Okay, so if we're using an LDA functional on an oxide, and we've really converged our basis set down to 10 to the minus 3 or 10 to the minus 4 EV, well, you're just very precisely predicting the wrong result, right? So it's not very helpful. You have to keep in mind everything. How accurate is my exchange correlation functional? How accurate is my basis? How accurate is my K-point sampling or my Brobine zone sampling? All of those things together as a kind of holistic accuracy is what predicts your experiment. Okay? So yes, make sure that your basis set is good enough, but no point going too accurate. It's just going to make it slow. Right? So in this case, what do I think is accurate enough? I think that this one is accurate enough, right? 7 times 10 to the minus 2. Okay, it's probably good enough. It's not perfect, but it's good enough. So what does that correspond to? Well, this first number is the difference between this one and this one. This is the difference between this one and this one. This is the difference between this one and this one. This is the difference between this one and this one, right? Okay, so basically by the time we get to this, right, which is 300, 400, 500, 600 EV, we're converged. Okay, so I'm going to write a note here, and I'm going to say 600 EV seems good enough for my purposes. Right? 600. So that's what I'm saying is converged in this case. The other thing to bear in mind here is when we ran this PD calculation, this palladium calculation, it made a pseudo-potential, right? It made a pseudo-potential. And that pseudo-potential, if we look at it, okay, it tells us predictions for what it thinks, or what Castep thinks is a good enough basis set. Right? And we can see that 600 EV is somewhere between what it calls fine and extreme. So we can see from that 600 EV is already pretty good, okay, even by Castep's prediction. Right, so we've done our basis set calculation. Now we need to converge with respect to the Brillouin zone, with respect to the k-point sampling. Okay, so what I'm going to do in this case is I'm going to copy this cell, and I'm going to paste the cell underneath this cell. Okay, so paste cells below, and I'm going to write a little title to remind myself what I'm doing. I'm going to write Brillouin zone sampling convergence. Right? And so in this case, what I'm going to do is I'm going to take out the cutoff energy. Okay, so I'm setting the parameter cutoff energy to be cutoff, but now I'm not setting it in the loop anymore. Now I'm going to set it outside of the loop because it's a constant. I've decided it's going to be 600 EV always. Okay, that's my converged result. But now I'm going to take the Brillouin zone sampling and I'm going to put that into the loop. Okay, I'm just going to modify the loop slightly because now I want to do k-point convergence. So the question is, what do I start at and what do I go up to? We've already said for a unit cell, gamma point in a crystal is not good enough. Right? 1 k-point is not good enough. We know that. However, we're going to start at 1 because let's prove it that it's not good enough. Right? How many is good enough? We don't know. That's why we're doing the convergence test. But let's try 6 by 6 by 6, see whether that's good enough. If it's not good enough, we'll have to go to 7, maybe 8, maybe 9, maybe 10. In some systems, you do not get convergence until you get 30 by 30 by 30 k-points, which is a huge calculation. An example of that is arsenic, or AS, on the periodic table. It has a very, very, how can I say it, quickly varying Brillouin zone, so it needs a very, very tight sampling. Okay, but most metals somewhere between 4 by 4 by 4 and maybe 12 by 12 by 12, depending on the metal. Okay, so we'll start at 6, and what we're going to say is we're going to have k-points, or the number of k-points, and energies. But if we do energies, then that's going to overwrite our cutoff energy data. So I'm going to call this energies k. Okay, so this is going to go from I equals 0 up to I equals 5 in Python. So maybe I'll say the range will be n plus 1, so that we do 1 by 1 by 1, 2 by 2 by 2, 3, 4, 5, 6. We'll do all of those. So what I'm going to do is I'm going to say k point equals I plus 1. We don't want 0 k-points. We want to start at 1, right? And we're going to set it like this. So we're going to have I space I space I. So in Python, all we need to do is convert our string k-point, right, into our integer k-point into a string. We need to add a space, and then we need to add k-point space, add k-point space. Okay, and that will give us 1 space 1 space 1, or 2 space 2 space 2, or 3 space whatever. So if we set that in our calculation, run the calculation to get the energy, and then put this data into our array, or our list, which is called k-points, right? Append k-point, and energies k, append energy. and then we're going to print K point energy, right? That should loop over all of these systems. Let's see whether it works. I think I'll also change the name, okay, because right now this is our old calculation. This is our cutoff calculation, PD PBE. I think I'll rename that one to cutoff. That's our cutoff convergence. And this one I'm going to call PD PBE K point. Okay, so let's run it and see what happens. So this star in Jupyter Notebook means it's running. Okay, and down here it says it's busy. Do we have a directory which corresponds to what we asked for the name to be? We do. We've got PD PBE K point, PD PBE K point in there. So this is where it's running our calculation. If we go into that directory, we can see we've got our pseudo potentials and we've got a cast-step output file. Okay. So what I'm going to do now, close some of this stuff. What I'm going to do now is I'm going to go into the terminal, AQT. I'm going to go into the terminal. I'm going to go into PD PBE K point, and I'm going to tail PD PBE K point cast-step. Right. And you can see here that the calculation is running. You can see we're running with 600 EV. That was our converged cutoff energy. And you can see right now we're running a 3 by 3 by 3 K point calculation. Right? Why are we doing 3 by 3 by 3? I thought we were doing 1 by 1 by 1 and 2 by 2 by 2. Because they've already finished. Okay? So if we scroll up, we can find that the previous calculation in this file is 222, and the previous one before that is 1 by 111. Okay? So they're all going into the same file. And we're just continuing this this loop. This is 444. Okay? And what we see is here, okay, we'll explain this later. What we can see is that the output is going straight to screen as well as into the file. And the output to screen tells us that our 111 gamma point calculation has this energy. Our 222 calculation is is about 10 EV different. Okay, which is a huge difference. Okay, it means that we are definitely not converged. So remember, our arbitrary tolerance that we're setting today is 10 to the minus 2, right? And this difference is 10 to the 1, right? Right. So by the time we get to 333, the difference between 222 and 333 is about 1. And then by the time we get to 444, the difference between 333 and 444 is about 10 to the minus, well, 3 times 10 to the minus 1. Okay? 0.3. So what I expect now is probably 555 or 666 will have good convergence. The difference between them will be less than 10 to the minus 2. Okay. What we also notice, unfortunately, is as we increase the number of K points, the speed of the calculation reduces. Okay, and much more dramatically than in the case of the cutoff energy convergence. Okay, so as we went from 200 EV or 300 EV up to 700 or 800 EV in the cutoff, there wasn't very much difference in the speed of the calculation. It was always fast. So really, it made very little difference whether we chose 300 or 700. You know, it really didn't make any difference. But in the K-point calculation, the 5 by 5 by 5 is still running. Okay, why is that? Well, the reason is because now we have cubic scaling. Okay, as we increase the number of the size of the basis, this scales linearly or quadratically, or at least it has a low prefactor in the scaling relation. However, this, no pen. Okay, I've lost my pen. This is not a pen. Oh, it's here. Okay, so remember that our Brillouin zone is 3D, right? Our Brillouin zone is 3D, and gamma point is there, and so that's 1 point, And when we go to 2 by 2 by 2, now we have a cube of points, right? Okay, so we've gone from 1 point to having a cube of points. Okay? And then when we go to 3 by 3 by 3, our cube of points is now 3 by 3 by 3. Okay, so it's cubically scaling. And this means as you add more, it gets much slower. Okay, because for every one of these points, we have to do another separate DFT calculation. Okay, this is one calculation. This is 8 calculations. 3 by 3 by 3, 27 calculations. This is why it's so slow. One thing to bear in mind is there is symmetry in this system. So there is time reversal symmetry, right? So because the Brillouin zone is a frequency domain, you can draw a line of causality, basically. You can draw a line straight through the Brillouin zone, and on that side, time is going backwards, and on that side, time is going forwards. So in physics, we know that it doesn't really matter if time's going forwards or backwards, apart from entropy. But we know that if we run the calculations backwards, it doesn't make any difference. Okay, so we can use this symmetry to our advantage. We can just do the points going forwards in time and just multiply by 2 to get the time reversal symmetry. Okay, so instead of doing 27 points in the case of 3 by 3 by 3, we only need to do 27 divided by 2 plus 1. Okay, plus 1 because of the gamma point. Right, so how's it looking? Well, we can see that the difference between 4 by 4 by 4 and 5 by 5 by 5 is about 0.1 eV. Okay, so it's not converged with respect to the arbitrary tolerance that we set, 10 to the minus 2. I expect 6 by 6 by 6 or 7 by 7 by 7. However, it's too slow for today, right? You know, I don't want to be standing here waiting for all of these calculations to keep running, and you just have to watch while I run a calculation, and then we just wait for it to run. So we're going to adjust our expectation. Okay, for the purposes of the class, we're going to say 0.1 is what we consider to be converged. Okay. In reality, you don't do that, because if you go to an experimentalist and say, right, I predict that you will have that your titanium oxide surface is going to have, you know, a surface energy 10 times higher than your other system. You know, this is my prediction, and then they measure it in their experiment, and they say, no, you know, that's garbage. Why are you telling me poor predictions? You know, the problem is that you've not converged your calculation, right? So just make sure that you do converge calculations in reality. In the class, we can take some shortcuts to make it go a little faster. Okay, and that's what we're going to do. So what I'm going to say in this case is that 4 by 4 by 4 will be what we consider to be converged. Okay, it's not terrible, because we can say it's converged to within 0.1 eV, not 0.2 eV. Not great, but you know, it's okay. So we'll get energies which will be within 0.1 error bar. Okay. Right, so there's our 6 by 6 by 6, and you can see that 6 by 6 by 6 is the one we would really, sorry, 5 by 5 by 5 is the one we should be picking, right? You can see the difference between 6 by 6 by 6 and 5 by 5 by 5 is approximately 10 to the minus 2. Okay, so basically 5 by 5 by 5 and 6 by 6 by 6 energy is the same to within 10 to the minus 2. So 10 to the minus 5 is good enough. Okay, but for this class, 10 to the minus 5 is too slow. So we're, sorry, 5 by 5 by 5 is too slow. So we're picking 4 by 4 by 4. Okay, all right. Let's write a note. So 6 by 6, 6 by 6 by 6, and 5 by 5 by 5 are the same to within 10 to the minus 2 eV. So we should pick 5 by 5 by 5 as our converged Brillouin zone sampling, right? Too slow for the class, so we will use 4 by 4 by 4, which has a slightly worse convergence of 10 to the minus 1 EV, right? Right. So, have you tried that? Yeah, and you got a similar result, right? You got a similar expectation, right? So, I don't know which system you tried, but this is when I asked you to try these calculations, this is what I would expect you would find, something like that. Okay, if you haven't tried it already, do it, do it, and you should. This is the kind of logic you should be using to decide which ones converge. Right. So now we want to do something with this. Okay. So what should we do? Let's make a surface, right? It's kind of arbitrary what we do with it. We could do a bulk calculation. We could, for example, do a band structure, or we could do a density of states, or we could do, I don't know, get a bulk modulus, something mechanical. We could look at some optical properties. Optical properties probably aren't that interesting for a metal, but we can do whatever we want with it, right? But I suggest we make a surface and look at some surface properties. Okay, let's try that. Let's make a surface. Okay, so what we're going to do is, instead of making a bulk system, now we're going to make a surface system. All right, so let's try it. So I'm going to say from ASC.build, import, and I'm going to make a surface. We know that this system is an FCC system, so we can cleave through the FCC crystal. Okay, so better than me drawing it is to look at a surface, look at an FCC crystal on this computer. Right, so I'm going to import one of the FCC surfaces, for example, 111. So let's put that in the background, and we'll say from ASC build import bulk to begin with, and we'll do from ASC build import make supercell. Right. What I'm going to do is I'm going to make the PD bulk again. So I'm going to say PD bulk equals bulk PD. Okay, calculation's finished. PD cubic equals true. All right, and that's going to give me my cubic cell. But now what I'm going to do is make a supercell out of it. So I'm going to say PD super equals I'm going to say make supercell PD bulk, and I'm going to have a matrix which is going to transform PD bulk into a supercell. What's my matrix going to be? So my matrix is going to be an identity matrix, and in NumPy and Python you can set up an identity matrix using I, just like MATLAB. Okay, and I'm going to say it's going to be a 3 by 3 by 3 identity matrix. And so, right, that's going to give me an identity matrix. Okay, so let's run that and see we get PD super. And because this is the identity matrix, PD super is going to be equal to PD bulk. Okay, let's look at the identity matrix just to convince you what it is. 1 by 1 by 1, sorry, 3 by 3 by 3 identity matrix. And so what we can do is we can multiply M by, for example, 3. And now we've got 3 down the diagonal. So I'm going to set my matrix equal to 3 by 3 by 3, 3, 3 on the diagonal. And now this is going to make a supercell, a 3 by 3 by 3 supercell of PD bulk. Okay? So what I'm going to do now is view it. I'm going to say from ASC visualize import view, and I'm going to view my supercell. So view PD super viewer equals ngl. Let's take a look at it. Right, so this is my FCC Palladium supercell. So what we've done is we've just taken a bigger piece of the crystal by repeating the conventional cell 3 times in each dimension. Okay, and I can change how many times I do that. I could do it 5 times, for example, and then I've got a really big piece of crystal. Okay, what's the point of doing this? Well, the point of doing it is just to see it, all right? Because right now I want to decide I'm going to make a surface from this crystal. Where am I going to cut? Okay, so you can see just by looking at this some cleavage planes, some places where I can cut. Okay, so for example, if I cut along the 1, 0, 0 axis, that means that I'm cutting through this axis, right? So I can cut across there, and then my surface will look like this, right? I'll have square symmetry on this surface, on the 1, 0, 0 surface. And equally, if I cut along here, this is the 0, 1, 0 surface. So these are symmetric, right? This is the same as this. This is the same as this. Okay. If I cut along the 1, 1, 1 axis, which is the cube diagonal, right? So it goes diagonally through the cube. You can see I'm going to get this hexagonal triangular symmetry like this. Okay. So the question becomes, which one do I want? Which way do I want to cut? Okay, it's going to give me different surface properties. Does anybody care, or should I just choose one? Nobody cares. All right, so we'll do 1, 1, 1. Yeah, let's do 1, 1, 1. Right. So what I'm going to do is take that stuff, copy and paste into the next cell. Right, and this time I'm going to use this ASC method, FCC111, to make the 111 surface. Okay. If I wanted a different surface, I could use the ASC surface method with some indices, some Miller indices, to cut any surface I want, right? But because I'm using a normal surface, something that's very common, FCC111, it already exists, so I can just make it. Right, so what I'm going to do here is I'm going to say PD surf equals FCC111 PD, right? And what I'm going to do is I'm going to give it just one argument. Okay, this is wrong. It needs more than one argument, and I'm going to show you a technique for finding what I need. Okay, so in the beginning, all I'm going to do is get rid of this stuff. I'm going to run this, and I'm going to see what's the problem when I run it. Okay, so when I run it, I see there's a problem, and it says I'm missing one required positional argument, size. Okay, so this is the size of my surface. Okay, all I need to do is put size in here. So let's put size in there. And what I'm going to do is I'm going to set size to be the size in x, y, and z. Z is how deep the surface is going to be. So to begin with, let's try doing, for example, 2 by 2 by 10, right? And see what happens. Okay, so when I run that, it seems to work fine. It seems to work. Let's see it. Okay, let's see it. Problem again. So what it says, if we go to the bottom, is we have a singular matrix. Okay, what does that mean? What it means is that we've cut through the 111 axis, right? We've formed a surface which is 10 deep, and we've stacked that surface directly on top of itself. The surface needs a gap, needs some vacuum between itself and itself. Otherwise, we've got atoms touching each other. Okay? You can't have atoms touching each other. It's not allowed, right? So what we need is a vacuum gap. Okay, so what I'm going to add here is another parameter, and I'm going to set this to be, I don't know, 5, right? We can specify units if we want. We can say from ASE units, import angstroms, and I can specify angstroms here. Okay, the 5 angstroms surface, and now I'll show you what I meant by that. Right. You can see we have a vacuum gap of 5 angstroms, 5 angstroms. Okay. If I make that smaller, you can see what the problem, the singular matrix was. So if I just make it, say, 0.5, right, you can see in this case, now we have almost no vacuum gap. You see the atoms are right next to the edge of the cell. And because we have periodic boundary conditions, because we have a plane wave basis, these atoms are basically in the same positions as these atoms. So they're touching each other. Okay? So that's no good. Let's set it back to being about 5 angstroms. Right? So this cell, 10 atoms by 2 by 2, is going to be slow to calculate on this computer, on four processors. It's going to be slow. So let's reduce our expectations a little, and let's, for example, run on 3 layers. So the third number, the Z direction, is the number of layers that we have in our system. Okay, so I'm going to reduce it to being 3 layers, and I'm going to have it as 1 by 1 by 3. Okay, and what you can see, hopefully, is that actually that is the same system. It doesn't look much like a surface, but because of periodic symmetry, because if we copy this in the X and Y plane, we will get a surface. This is just a surface unit cell. Okay, and I can prove that to you if we do exactly the same trick we did here, but with the surface cell. Okay, so what I'm going to do is I'm going to do a supercell of the surface. Right, so I'm going to say my supercell surface is equal to the supercell of the surface. Right. Now, the problem with doing that is now that's also going to copy my surface in the Z direction. Okay? We're not interested in the Z direction, we're only interested in the X and Y direction. Okay? So what I'm going to do is I'm going to make my what do I call it? Make my 3-3 index of the matrix 0. It's easier to just show you that. Right. If I just print M, right. If I print M, what we can see is it's 5, 5, 5. It's 5 multiplied by the identity matrix. But I want to make this point 0. Okay, so I'm going to set that equal to 0. And you can see I've got 5, 5, 0. Okay? 0, 1 is what I want. Right? 5, 5, 1. So now I'm going to view that, and we can see I do indeed have a surface. All right? So my surface is 3 layers deep and looks like a surface. Right? So I'm just proving to you that this is a surface, even though it just looks like 3 atoms. Right? Because of the shape of the cell, it is a surface. Right. That's a lot of speaking and not a lot of calculations. So what we need to do is do our calculation on this system. Okay. So what I'm going to do is calculate our previous calculation. So sorry, copy our previous calculation and paste it down here. And I'm going to do that calculation on the surface. Right. So I'm going to say this is called PD, PBE, surf, the surface. Okay. I do not need this line because I'm not doing the bulk calculation, but I do need this line because I'm doing the surface calculation. All right, so I'm going to stick my surface calculation down here. I'm going to get rid of all of this stuff. And so I just have these 2 lines from ASC build import FCC111 and PD surf equals FCC111. Put that up here for neatness. All right, so that's the calculation I'm doing. PD surf. I'm doing a cast-up PV calculation, cutoff energy of 600, and we said that we were going to do a 4 by 4 by 4 Brillouin zone sampling. Right? So I'm going to say that my K-point NP grid is 4 by 4 by 4. However, because we're doing a surface, right? Because we're doing a surface, we can see in this direction, in the Z direction, we have no symmetry. Okay, we've broken all symmetry. What we're supposed to be having in the Z direction is just infinite vacuum. Because of periodic boundary conditions, we don't have infinite vacuum. We just have 10 angstroms of vacuum, right? But it breaks our symmetry. So all of those arguments we were saying about Brillouin zones, and in a crystal we can have very low frequency electron waves, and those cannot be represented in a unit cell, and so we need to add block waves, block states in order to get the correct crystal physics. In the Z direction, we don't care about that, right? Because we don't have a crystal in the Z direction. We've broken the crystal symmetry. That means we can play a nice trick, and we can say in the Z direction, we have gamma point symmetry. We get rid of our K point in the Z direction. Okay? So that's basically our calculation. We're not doing a loop right now. So what I'm going to do is get rid of all of this stuff. Right? All I want to do is do a simple calculation of that surface. Right? So I'm going to say that. Right? I've got a calculator. I've got PD surf. I put the calculator in PD surface, and I run the get potential energy method on PD surf. Okay? So together, that should run my cast-up calculation. So let's come out of here. Make sure that it's made a directory. I can see PV surf, and in here I can go CD PD PVE surf, and I can tail that calculation PD PVE surf cast-up, and I can see that it's running. Okay. It's not fast, it's not slow, it's running. Okay. One thing to bear in mind, we can see that there's a warning here. Okay? The warning says there's no empty bands for at least one K-point and spin. Okay? So, what are bands? Bands are, I think we said this on Monday, but if I didn't, bands are just the allowed regions of energy in our Brillouin zone. Okay? So, if we go to a K-point, if we go in the Brillouin zone to this K-point, and we ask the question, if we solve the Kohn-Sham equations at that K-point, then when we solve the Kohn-Sham equations, our eigenvalues are the energies of our bands at that point. Okay? We solve it at this point, we get the eigenvalues at that point. Right? So the bands are basically the states or the orbitals in molecular orbital theory, but in solid state, in crystals, the bands are like our periodic orbitals, just our states, right? And the problem we had here is that there were no empty bands. And that means that, why do I keep doing this? Why do I keep doing this? I keep putting it there and confusing myself. Right, so if we think about our Fermi-Dirac distribution, what this is saying is that there exists some bands in our system where at the top of the energy range, we still have some electron. Right? In our calculation, we should have enough bands that the very top bands have 0 electrons. Right? Otherwise, we're cutting off some electrons. Okay? However, in the next iteration, we can see that it did not complain about empty bands. So this was only a problem for the first iteration, and then it went away, so we can ignore it. If it complains about extra bands, then we would need to do something about it. So we would need to add a parameter like n extra bands. I don't know what it, oh yeah, n extra bands. We need to do this in the input file. Because this error has gone away, or this warning has gone away after the first iteration, we can ignore it, and we don't need to worry about it. Okay? Right. Just enough speaking to finish the calculation, and we can see our calculation is finished in just under 1 minute, and we got an energy which we can print out if we just type energy, and it warns us that we got a warning in the calculation. That's the warning I said about the extra bands. And you can see it just copies and pastes that warning. There are no empty bands for at least 1K bond spin, but we checked the output file, and we saw we only got that on the first iteration, not again, so we can ignore it. Okay, we don't need to worry about that. Right, so that's our surface energy. If we want to do a converged surface energy, we then have to worry about converging our surface. Right? Can I just turn this over? Oh, that's better. Right. So what we have to remember is when we've got our surface system, right, which looks something like that, and of course it's copied in space. What we have to remember is this is an approximation, right? This is an approximation to the infinite crystal. If I have a piece of palladium, a piece of palladium this big, okay, if I have a piece of palladium this big, I'm extremely rich, right? But let's say I've got a piece of palladium this big, right? And this is my palladium 111 surface, okay? If I look at the thickness of this piece of palladium, it's macroscopically thick, right? And it's of the order of, 10 to the minus 1 meters thick, right? Let's say it's of the order of a meter thick. That means that the number of atoms that we have in the z direction is of the order of 10 to the 23, 10 to the 24, 10 to the 25 atoms in this dimension, right? We have an effectively infinite number of atoms with respect to our 3-atom thick calculation. Okay? That also means that this distance from the surface to infinity is also effectively infinitely thick compared to that, right? So we are trying to approximate a piece of metal which is effectively infinitely thick with 3 atoms, right? And we have vacuum on both sides. What's the implications of that? Well, the implications of that is we don't have a very good surface, right? So if you imagine that if you go all the way into the middle of this metal, and it's bulk positions of the metal, bulk FCC, you go down, right? Bulk positions, it's just like bulk palladium right in the middle. On the surface, you can get surface relaxation. You can get geometric surface relaxation, like surface reordering, maybe the atom moves around on the surface. You can get electronic surface reordering, like the Smolakowski effect, which basically means if I have a sharp amount of electron density, because I've got a dangling bond effectively in chemistry language, then that just means that area of negative electron density will fill in this part, right? Smolakowski effect, surface reordering, all of these things can happen on the surface. However, if I have three atom thick surface, it will happen on that side as well, right? And that means that my surface here, which I don't want to be a surface, is not very bulk-like. It's surface-like. So my surface here, what I want to be the bulk deep inside of the palladium is actually like the surface. And so my physics is going to be very poor because I have surface-like electrons in the bulk position. Okay? So what I can do is I can add more atoms. I can say, well, how about I have 5 atoms? If I have 5 atoms now, I can say that this atom is more like the bulk atom. Okay? And then if I add even 7 or 9 atoms, this atom is more like the bulk atom. Right? eventually, if I have enough atoms, it's a good enough approximation of the macroscopically thick surface, right? But I don't know how many atoms I need in order to get the correct surface properties before I've done it, right? 3 might be enough. 5 might be enough. Or maybe 11 is not enough. We just don't know. It's the same as convergence in anything. But this is why what you have to do is a convergence test again, right? Basically, once you start doing DFT calculations, plane wave DFT calculations in physics, okay, I don't think we have any chemists here, maybe, right? But I don't want to insult the chemists, right? People who do chemistry, because they do some good work, but chemists do not care as much about accuracy, in my experience, okay? Physicists tend to care more about getting a very accurate answer. So when physicists do DFT calculations, they do convergence test, convergence test, convergence test, convergence test. Make sure everything is as good as possible, right? This is a different strategy from what chemists tend to do, which is, maybe I'll use 6,3G star. That's good enough. Run it. This is my answer. It's a different strategy. Generally, physicists will make sure that everything is very, very carefully converged. And although it takes longer, it gives you more confidence when you speak to an experimentalist, that you can argue with the experimentalist and you can say, well, you're wrong, right? My calculation says that you should be seeing this. Do your experiment again, right? Whereas if you go in with a calculation which is not converged and the experimentalist says, I don't think that's right, then you have to say, well, maybe it isn't. I should go and do another calculation, right? So more convergence tests. More and more and more, right? The other thing that could be affecting our results, which we might need to converge with respect to, is the vacuum, right? Because you remember, we've got a big space vacuum there, we've got a big space vacuum here, right? And that atom has a big piece of, in chemistry language, it has a big dangling bond sticking off it, right? It has a load of negative electron density, which is just kind of floating there. That means we have a partial negative charge, probably, depending on surface rearrangement. But we have a partial charge on the surface. And we have another partial charge over here on this surface. And so, because if we go up, 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 periodic boundary condition, we come back up through the bottom, right? That means that we have an electrostatic interaction between this atom and this atom. They effectively are pushing each other apart electrostatically, right? We have two charges and they're pushing each other apart, okay? This will affect the result, and it will mean that potentially we get the wrong result. If we make this bigger and bigger and bigger, the electrostatic interaction will decrease very quickly. But, as you know, the dipole order term will not decrease so quickly, right? The dipole order will take longer to decay. And so we may still have dipole interactions between the top and the bottom, even when we have a large vacuum gap, okay? If we have a charged surface. This is something we have to bear in mind, but it's something we can fix by doing a convergence test, right? So converge, converge. So what do we need to do? We need to do a convergence test with respect to the number of atoms. Let's just write this down. So we need convergence tests. I should say more convergence tests with respect to number of layers, with respect to vacuum gap. Okay? So let me just quickly do a couple of those, right? I'm not going to do a really comprehensive convergence test because we don't have a lot of time, but let me say I'm going to do vacuum gap. Just easier, right? It's quicker, right? So what I've got here is vacuum here is 5, and so what I need to do is to bring that into my loop. Okay, so if I do for I in range n, okay, as before, same loop, and I do say 4, 3, 4. Okay, four calculations. What I'm going to do is say my vacuum equals, and what does my vacuum equal? Well, we could have 2, 3, 4, 5 angstroms. Okay, let's do that. Okay, so we're going to have 2 angstroms plus I times, plus I times 1.0. Okay, why have I done 1.0? Because this is an integer, I just want it to be, never mind. Okay, so what I'm going to have here is 0, 1, 2, 3. Okay, it's going to be my loop index, it's going to be I, and I'm going to have 2 plus 0, 2 plus 1, 2 plus 2, 2 plus 3, and so I'm going to go from 2 to 5 angstroms vacuum, right? And so I'm going to stick my vacuum in here. Vacuum equals vacuum times angstroms, and I'm going to run that calculation. Okay. What I need to be careful of is that now I'm making a new calculation each time I'm changing the vacuum. So every time I make a new calculation, it no longer has the calculator attached to it. So I need to make sure that I attach that calculator to this calculation. Dot calc equals calc, right? And now I can run that, but I'm going to do exactly the same as I did before. Maybe I can be quicker by copying and pasting. And I'm going to do something like this, right? Maybe something like this. I'm going to store that data. So I'm going to say not k points, but vacuums equals vacuum, and energies V for vacuum equals energy, and I'm just going to have 2 lists here, which I'm going to call vacuums equals an empty list, and energies V equals an empty list. Right. Finally, I'm just going to print out in this loop that. Okay, and then we can try running it. Right. Try running it and see what happens. Okay. So what we remember from the vacuum calculation we just did was the first one, which had a vacuum of about 5 angstroms, took about 1 minute. Okay. This first one has a vacuum of about 2 angstroms on both sides, so it should be much quicker, maybe 20 seconds. Right? So we should be getting something like 20 seconds. Vacuums. Okay. Just misspelled vacuums. Okay, let's run that again. So what we should be finding is that we'll have a calculation which is quite quick in the beginning, and then we'll have a calculation which is slightly slower, slightly slower, slightly slower, but it will be linearly slower, okay? Because we are only increasing the size in 1 dimension. Unlike the k points where we're increasing in 3 dimensions, in this case we're just increasing in 1 dimension. So it should be relatively fast. Okay? Right, but we'll just allow that to run, and I think, why don't we have a quick break, and then when we come back, you can do some calculation, and we'll do we'll decide what to do. Okay, so I also want to give you the chance to sort of suggest things to me, right? You know, if you particularly want to do a particular kind of calculation or are interested in particular kinds of calculations, if it's feasible to do it within the class, we'll do it, right? I mean, if you say to me, I want to do a GW calculation of a 10 by 10 by 10 angstrom cell, you know, and I want to calculate the, you know, the excited state, the excitation energy of a plasmon, or you know, probably we don't have enough time to do that this week, and it's a bit complicated to do it in this time frame. But if you said to me, I'm interested in the bulk modulus, or I'm interested in surface energy, or work function, or I'm interested in binding energy, binding strength of a molecule on a surface, something like that, we'll try to do it. Okay? If you don't say anything, I think we'll probably do binding energy, I guess. Yeah, we'll just pick something. All right? Anyway, have a short break. I'll have a drink, and then we'll come back in 5 or 10 minutes.